this is a good moment to see a closely related topic. So we saw the existence and uniqueness of solutions theorem. So let us have a quick relook. So consider the differential equation x dot is equal to f of x, where f is a map from Rn to Rn, and at the initial condition x naught, suppose f is locally Lipschitz, then there is a delta greater than 0 such that there is a solution, and there is a unique solution in fact, x of t to the differential equation x0 is equal to x naught for the interval 0 to delta. So please note that we are starting from t equal to 0 to some delta greater than 0. So this is an interval in positive time for the future. So there is a solution, a unique solution for some time in the future. An important question is there a unique trajectory in the past? So what about existence and uniqueness of a solution in the past? So for this particular issue, we can easily modify our theorem. So replace t with tau with the by defining tau equal to minus t. So as t evolves into the future, tau evolves into the past. So the differential equation x dot is equal to f of x becomes d by d tau of x equal to minus f of x. In other words, d by d tau of x of tau, x is a function of tau now, is equal to minus f at x of tau. So how does one obtain the vector field for this dynamical system? We just reverse the direction of all the arrows in the vector field of the differential equation x dot is equal to f of x. Why? Because each arrow is not f of x but minus f of x. So if f is Lipschitz, notice that minus f is also Lipschitz. Hence the Lipschitz condition on f guarantees existence and uniqueness of a solution in the past also. So what are the implications of this particular observation? So two solutions x of t and y of t cannot meet at x final if at a point x final if f is Lipschitz at that point x final. If f is locally Lipschitz at x final, then it is not possible that there are two past trajectories x of t and y of t which have the same final condition x final. Similarly, autonomous systems, everything that we have been doing so far is for autonomous systems. One of the properties that we can claim about autonomous systems is that the autonomous systems cannot reach the equilibrium point, the equilibrium state in finite time. Why? Because whenever it reaches an equilibrium state, that equilibrium state already had one past which was the same point for all time, but there cannot be another trajectory that comes and meets this equilibrium state if f is locally Lipschitz at this equilibrium state. So if you want to have a particular system, if you want to design a controller in which you reach the steady state in finite time and remain there, then one would require non-Lipschitz controllers or plant transfer function to reach the equilibrium. In this case, we interpret the equilibrium as the steady state. If you want to reach the steady state in finite time, then one would need either non-Lipschitz controllers or non-Lipschitz plant transfer function. Why is that? Because with Lipschitz, we can reach the steady state only asymptotically. It is not possible to reach in finite time. Okay, so another important topic is we have been seeing only local existence and uniqueness conditions. What is local about it? We saw that there exists a solution and it is unique only for an interval 0 to delta. Even existence could not be guaranteed for large enough time, but it could be guaranteed only for a time interval 0 to delta. All that was guaranteed was that delta is greater than 0, but it is possible that this delta is a very small value and we are unhappy with this result about the existence and uniqueness for so small an interval possibly. So it is possible that can solutions exist over the interval 0 to infinity? Is it that the solutions indeed exist and they are unique, but our theorem is not able to guarantee it? Is the theorem too harsh? Is it that it is assuming locally Lipschitz property on f, because of which we are able to guarantee existence and uniqueness only for a small interval 0 to delta, but there might be some other result, some other way of proving that the solutions exist from 0 to infinity. So, are the conditions assumed in our theorem too harsh, because of which we are able to prove only local existence and uniqueness? For this we will see one small example. So, it is indeed true that sometimes solutions indeed exist for only a finite time. So, our theorem can also accordingly claim existence and uniqueness only for a short interval. Why would they exist for only a finite time? Because it is possible that the solution becomes unbounded in finite time. So, consider the differential equation x dot is equal to x square, where x dot is equal to x square means that f of x is equal to x square. So, notice that this is Lipschitz, yeah? In fact, it is locally Lipschitz at every x naught in R. So, please note that this dot here does not mean it is multiplication of x square and f of x, it is the end of a sentence. X dot is equal to x square is the differential equation, and for this differential equation f of x equal to x square, and this particular function f is locally Lipschitz at every point x naught. But notice that one Lipschitz constant does not work for the full R. Yeah. So, we can explicitly solve this differential equation x dot is equal to x square to get dx by x square equal to dt, and upon integrating both sides we get x to the power minus 1 divided by minus 1 equal to t plus some constant c1, and upon rearranging this minus 1 and x of t, we will call minus c1 equal to c2, and we get x of t equal to 1 over c2 minus t. So, when we put the initial condition at t equal to 0, suppose it was at x naught, x 0, then when we substitute we get x of t equal to 1 over x naught minus t. So, let us just make this. So, our differential equation solution, this is how the solution to our differential equation looks. Okay, so let us see what this means. If x of 0 is equal to some number, let us say 4, then we see that x of t equal to 1 over quarter minus t. So, we see that for t equal to 0, of course, it is equal to 4, and as t tends to 1 by 4, this quantity becomes unbounded. So, a graph of x versus t, x starts from 4 and it becomes unbounded. So, within a small interval up to 1 by 4, already it is so large that it is unbounded. So, we have solutions defined only over, for this particular initial condition, we are able to define existence of a solution only from 0 to 1 by 4, while it is a closed interval on this side, it is an open interval. For t equal to 1 by 4, we do not have a solution to, this solution does not exist. So, what we have seen is, when the initial condition is equal to 4, we had solution only up to 1 by 4. Suppose the initial condition was equal to 1, then we have a unique solution for some delta, but when we try to increase this delta, we see that x of t exists and is unique. How long can we extend this? We see that by explicitly solving this differential equation, we get x of t equal to 1 over 1 minus t. So, x t is defined, exists only for t in the interval 0 to 1. 0 to 1 for this particular initial condition. So, for each initial condition, it becomes unbounded in a finite time. In how much time it becomes unbounded, that time depends on the initial condition. So, a set of solutions to this differential equation. If it starts below, then the solution exists for some more time. If If it is at 0, of course, it remains at 0 for all future time, because it is locally Lipschitz. At 0, the solution cannot emanate out of the equilibrium point. There is a unique trajectory and hence it remains always at 0. But if x of 0 is negative, then what happens? X of t is equal to some number 1 over x naught, which is negative, minus t. So, the solution always exists. So, when it is negative, then we see that the solutions are coming close by. So, we see that if x of 0 is negative, then the solutions exist for all future time. They are not becoming unbounded in finite time and they are all approaching 0. But if x of 0 is positive, then the solution grows and becomes unbounded in a very short time, in a finite amount of time, and hence we cannot have global existence of solutions when initial condition is positive, but it appears we can have global existence of a solution when x of 0 is negative. So, it appears like for certain situations there do exist solutions from t equal to 0 to infinity, while there are other situations for the same differential equation, there are certain other initial conditions for which the solutions exist for only a finite amount of time, in which case we cannot have global existence of the solution, let alone global uniqueness. So, for this particular differential equation, we might have some additional assumptions under which we have a unique solution from 0 to plus infinity, and it is possible that for certain initial conditions, those conditions of the theorem do not hold, in which case we do not have global existence. So, those additional conditions, how to formulate them is the topic we will see in the following lecture. Okay, thank you.